This is Stephen Yan presenting Lab 4. The purpose of the lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet and tube interactions computationally, and compare the results. Physical principles of the lab include magnetic flux, which describes the total magnetic field passing through an area and normal to the area. The reason to use this is that it's a key component in using Faraday's law. Next, there's the Faraday's law, which relates the induced voltage to rate of change of magnetic flux. We include this because it allows later calculation of the force generated by the aluminum foil. Finally, there's Lorentz law, which determines the direction of the induced current. This gives the direction of the force generated by the coil. Here is a brief overview of the results. The system being studied includes the aluminum foil, the bar magnet, and the Earth because of gravity. For the physical model, a magnetic dipole is dropped into a cylinder composed of rings of conductive coils, as shown in Figure 3. The reason to use this model is because the bar magnet can be approximated by a magnetic dipole, and the cylinder of aluminum foil is modeled as discrete coils stacked together in order to simplify the simulation of current in the foil. We assume the experiment is done on Earth, meaning gravity is 9.8 meters per second squared. We assume that the only change in magnetic flux is caused by the moving magnet. We assume there's no friction and no air resistance. Finally, we assume that the resistivity of aluminum foil is constant. Here are the initial conditions for the experiment. The results for each trial is shown below. They average out to be around 0.56 seconds. During the experiment, I observed that the magnet appears to be floating inside the row. Its downward acceleration is smaller than if it was dropped in free space. Let's now move on to the coding section. Most of the code has already been provided. I first have to specify the measurement of the row of aluminum foil, as shown below. Next, I will input the property of the magnet, including its mass and magnetic dipole moment. Once executed, the result is shown on the right. As we can see, the time in the tube is predicted to be 0.268 seconds. By comparing the similarity and differences between the data and model predictions, we find that the results from both the experimental data and simulation showed that the magnet indeed descended more slowly in the aluminum foil. However, quantitatively, the experiment showed that the magnet descended slower than in the computational prediction. This can be caused by friction between the magnet and the inside of the aluminum roll, or that the roll is not held perfectly in a vertical orientation. To conclude the report, I would like to discuss two what-if questions. First, if the resistivity of the conductor were reduced as close as possible to zero, Ohm's law will predict that the current in the foil will approach infinity, meaning the magnet would be stationary inside the aluminum foil. If holes and slots were cut into the tube, some rings in the model would no longer constitute complete circuits, meaning the entire cylinder would generate less force on the magnet, which causes the magnet to fall faster.